Hi folks, and welcome back to Physics with Captain Rod. I'm making this video to help you out with numbers 7, 8 in your Unit 3 homework. 7 and 8. Alright, so number 7, calculate the force needed to bring a 1,050 kilogram car to rest from 85 kilometers per hour in a distance of 130 meters. So, here's just kind of a quick picture of our problem. Here's our car and it's moving this way. And it's got a velocity, I'll just call it V, which is given in the problem. Now they gave you a number in kilometer per hour. Mine says 85 kilometer per hour. First thing I would do is take this, and no doubt we're going to need this in meter per second. So there are 1,000 meters in 1 kilometer. That will help you out, and there are 3,600 seconds in 1 hour. That should help you with the conversion. Now, the car moves along and it slows down to rest. So remember the motion diagrams, the kind of, I always call them the snapshots in time that kind of show the car slowing down, right? And that's why the distances between the dots is getting smaller and smaller and smaller. And this can be attacked using principles of work and energy. So you write out the work energy theorem. PE1 plus KE1 plus work equals PE2 plus KE2, the big, long, ugly theorem. Now, just some aside notes on what this stuff is all about. So for your homework, right, the potential energy terms are always going to be MGH terms. And then the kinetic energy terms are always going to be 1/2 mv squared terms. And then the work term is always going to be force times distance. So when we look at this problem, you notice that there's no changes in height. So there's no changes in potential energy to worry about. So you can think of it like this. If we put our datum right through here, all the potential energies are 0. This problem just isn't a potential energy problem. So you can put zeros here and here. Okay. For KE1, you put 1/2 mv squared. And that's for the kinetic energy of the car at this location. For KE2, you're going to put 0 because here's position 2. The car's not moving anymore. It's stopped, so it has no kinetic energy. Now the work term, remember work is force times distance. So I'm just going to put force times distance here. Now, the nature of the force, all right, in this example, the car's applying the brakes. That's going to create what's called a frictional force, and that force is going to be in this direction on the car. And the car's moving to the right. So here's an example where the work term is negative. So this is going to be minus here. And then there's my equal sign. Now just put in all the values that we have. And I think this is an unknown in the problem. You should be able to find that force. Okay. Part B, it says, suppose the car hits concrete and is brought to a stop in 2 meters. For part B, basically you're going to do the same thing. You're going to write the same equation out. You're just going to use a much smaller distance here for D, and then you're going to calculate a different force value, and it's going to be much larger. And then they're asking you basically to take the force that you calculated, let's see, in part B, and divide it by the force that you calculated in part A, and you're going to get a number. It'll probably be like 100 times larger or something like that. So anyway, that should get us through number 7. Whoops. Yeah, we'll clear that out. And we'll clear this out. All right, number 8. Let's see, a car's bumper is designed to withstand a 6.48 kilometer collision. The car's bumper absorbs the shock over a distance, and it says that the distance is 0.3 meters. And the mass of the car is given, and the initial speed is given. So it's very, very similar to the last problem. We have a car. I know it's a really crummy car. I'm just going to do this for the bumper. And here's our position 1, and the car's moving to the right. And it's got a speed given in the problem. Mine says 6.48 kilometers per hour. Yours may say something else. Similar to the last problem, you're going to want to convert this to meter per second. And then in position 2, the bumper is like crunched, right? And like here's where it used to be. And this is the distance that you're going to use for the work term. The force was applied to the bumper basically like this, crumpling it over this distance. So when you write out the work energy theorem, PE1 plus KE1 plus work equals PE2 plus KE2, there are no potential energies to worry about in this problem. You will have a KE1 that you're going to get from the mass and from this speed. The KE2 is 0. And the work term, very similar to the last problem, is minus force times distance. Now, the force times distance that's how work is calculated. And the minus sign is because when this car hits this object, the car is moving to the right, but the force on the car is moving to the left. That's why the work is negative. Anyway, that should get you through number 8. I hope that this helps. Have a great day.